Okay, we are discussing about the metal casting operations. Today we are going to discuss about the calculations related to the metal casting process. Okay, let's move to the theory under this topic. Okay, in this lecture we are going to discuss some calculation related to the metal casting operations. Okay, metal casting operations. Okay, first of all we are going to discuss mold filling time. Okay. Mold filling time calculation. Okay, mold filling time. So mold filling time mean in when molten metal pouring, what is the time taken to fill the complete cavity of the mold is called mold filling time. That mean let me take this kind of a mold. Okay, let's take this is the sprue of the mold. This is the sprue where the molten metal poured to this sprue. Then it is passes to the main runner. Then it enters to the cavity area. Let's take this is the cavity area, the product cavity area. Okay, this is the cavity area. Okay, this is called the product cavity. Product cavity. Then let's take the volume of the product cavity as V. Total volume of the product cavity as the V. Okay, cubic inches or cubic centimeter. Okay. Then let's take this is the main runner. Let's take the main runner cross sectional area as A. Main runner cross sectional area as A. Okay. Then mold filling time. Yeah. Let's take where the molten metal poured to this sprue in pouring. Okay, molten metal. Okay. Then it fills like this. Then this molten metal passes through the main runner to the cavity because of the gravity force. Okay, because of the gravity force. Okay, because of the gravity force, it passes to the cavity. Then the air trapped in the cavity escape through the vent hole. Okay, escape through the vent hole. Okay, this is what happened in molten metal pouring. Then in gradually filling the mold, the air trapped inside this mold escape through the vent hole or open risers. Okay, open rise. If the open riser is there, the air can escape through the open riser. Okay. Then what happened? This mold filling time mean to fill this complete cavity. The time taken to fill this complete cavity in pouring is called the mold filling time. This that mean when to fill the complete cavity, that time taken is called the mold filling time. The M F T. Okay, mold filling time. So this time calculation is very important to ensure the cavity has completely filled with the molten metal in pouring. Okay, this calculation is very important to ensure the mold cavity has to fill with the molten metal in pouring. Okay, that means if mold, let's take for example the in calculation, let's take we got the mold filling time as the 5 minutes. Okay, for example, when it pouring, when pouring the molten metal, if we notice it has the there's no further flow through the sprue molten metal. There's no molten metal flow through the sprue in a 3 minute. What it means? What it means? There's a block in a main runner or any entering gating system. That means mold has not filled, cavity has not filled completely. Okay, the most probably with the less mold filling time having the defects. Okay, misrun defects. Okay, so this if it take the 5 minutes exactly, we can ensure the mortar metal fills entirely in this cavity area. So that is this mold filling time is that's why the mold filling time is important. Then let's see how to calculate that mold filling time for a certain product. Then this for certain product, certain casting operation, V is a known value. V is a known value. Product cavity volume is a known value. Okay, we can easily calculate the product volume also is a known value. Is a known value. Then A also known value. Main runner dimension is a known value. Main runner dimension is a known value. Okay, known value. A is a known value. Then if we know the we can write simple equation. Mold filling time is equal total volume of the cavity area divided by flow rate Q dot through the main runner. Mortar metal flow rate Q dot through the main runner. If you know the Q dot, we can easily calculate the mold filling time. But how to calculate the Q dot? Q dot is equal A into U. A means the cross-sectional area of the main runner and U is the mortar metal velocity through the main runner. Okay. If you know the Q dot, we can easily calculate the mold filling time by dividing volume by the Q dot. Then how to, A is a known because is a known dimension when you are designing the runner system. A is a known value. Then how to calculate the U? If U is known, we can calculate the mold filling time easily. Okay, then how to calculate the U? Okay, to calculate the U, we are going to use Bernoulli's theorem. Okay, you may learn this Bernoulli's theorem in Bernoulli's theorem in your A level. The Bernoulli's theorem we are going to use. We are going to apply this Bernoulli's theorem to this continuous flow. So we can apply the Bernoulli's theorem we can use for continuous flow, incompressible continuous flow. We can apply two distinct points. We are going to apply. That means we are going to apply this Bernoulli's theorem to these 2 points. Let's take this point as point 2. Let's take this point as the 7 point on the main runner. Let's take it as the point 1. These two different points we are going to apply the Bernoulli's theorem. Then what is what the Bernoulli's theorem says? Bernoulli's theorem says the for continuous flow, incompressible continuous flow, the half into rho V square plus rho GH plus pressure is a constant. Assuming no frictional losses. Okay. For this calculation also we are ignore the frictional losses. Okay, frictional losses. Okay, keep remember that one. The frictional losses we are going to ignore for this calculation. Okay, then I am going to apply Bernoulli's theorem for these two distinct points, the point 1 and point 2. Okay, let me apply this Bernoulli's theorem for the point 1. How to write the point for the point 1? We can write Bernoulli's theorem half into rho. The V mean the velocity through that point. Let's take that velocity we took as the U. No, let's take the U1. Yeah, U1 is square plus rho G. The height. The height mean from a reference level. What is the height for this point? Let's take it as the height as h1. For this point, let's take it as the height is h2. from a reference level. Okay, from a reference level. Okay, we are measuring. Let's take this is the reference level. Okay, rho g h1 plus pressure. Let's take the pressure at this point as the P1. Pressure at this point as the P1. Then a constant that is equal to half into rho U2 square plus rho GH2 plus P2. Okay. In this way we can apply Bernoulli's theorem for these 2 points. Okay. Then we can further simplify this equation. Yeah. I will take P1 minus P2 into one side, half into rho U1 square plus rho, then I am going to take G, the H1 part I am going to take in this side, G H1 minus H2, then I am going to take P2 in this side also, P1 minus P2 is equal half into rho U2 square. Okay, U2 square. Then in this equation, the what is mean by the P1 minus P2? What it means? P1 minus P2. P1 minus P2. What is the value for the P1 minus P2? P1 minus P2. P1 minus P2. What is the value? P1 minus P2 is equal to 0 because it is an open flow. Because it is a open flow. That means open flow mean what it means. What I mean. For example, you may think how it is equal to 0. Let's take this kind of water column. If the water column flow is restricted, let's take the 2 different point 1 and point 2. There's a pressure difference. If the flow is restricted, then in static condition, if the flow is in static condition, there's a pressure difference delta V is equal to rho GH. But if we open in bottom, what happens is a free falling water column. No? Free falling water column. There should no pressure difference in between the 2 different points because it is a free falling. Because this pressure at 1.1 because of the weight of the this water column. This pressure at the point 1 is developed because of the weight of the this water column. But if it is a free falling water column, there is no wave acting on this point 1. So that same as in here, it's a flowing. There's no restrict to this flow. It is flowing. So the pressure difference is equal to 0. This term is equal to 0. So we can put the 0 in here. Okay. Then what happened? Then this equation we can write. We can reduce actually half into rho U1 square plus rho G H1 minus H2 is equal half into rho U2 square. Then the rho is a common term now, that we can cut easily rho. And H1 minus H2, I am going to put this height difference, let's take it as the H. Okay, let's take it as the delta H. Yeah, delta H. So then we can further reduce this equation. H1 minus let's take H2 minus H1 as the delta H. Okay, let's take H2 minus H1 is equal to delta H. This height difference as delta H. So this is equal to minus G delta H is equal half into u2 square half into u1 square. Okay, this equation is reduced to in this kind of format. Okay, so then what happened, in this calculation, comparing to the, let's take this is a1, let's take this as a2, a1 and a2. This a1 is very small comparing to the a2, so that u1 is very small comparing to u2. We can consider u2, we can consider u2 as the 0. That means when applying the Bernoulli's theorem, that is called the reservoir velocity. Reservoir velocity we are equating to 0 because it has the larger surface area, so that the reservoir velocity we are taken as the 0. You may remember in your doing the A level, you may take the reservoir velocity as the 0 when applying the Bernoulli's theorem. So we are going to equate this one to 0. So then the equation is reduced to u1 square is equal 2g delta h. Okay, then you can easily calculate the u1. u1 is equal 2g delta h into square. Okay, delta h into square. The delta h means the main runner to the that is called the sprue height. The actual the delta h means the sprue height of this sprue. The 2g delta h is inside the square root 2g delta h is equal to u1. If we know the u1 velocity through this motor metal velocity through this main runner, we can calculate the q dot, and also we can calculate the mole filling time. So then I'm going to calculate that one. We can write this equation. Mole filling time is equal V, the total volume of the product cavity, the q dot is equal AUV, A into u1, the 2g delta h into square root. Okay, this is the equation we are going to use to calculate the mole filling time in metal casting. Okay, mole filling time in metal casting. Okay, then you can see this is called the total volume of the product cavity. A means the cross sectional area of the main runner. Then inside the square root 2g delta h mean sprue height. Okay, sprue height. This is how we are calculating the mole filling time in metal casting. This calculation is very important. We are ensuring this mold has filled completely by looking at this mole filling time. Okay, mole filling time. If it is taken the less time to fill the less time than this mold, this calculated time, that means mold has not completely filled with the molten metal. Okay, this calculation is very important. Okay, then let's take the example from this mold filling time. Okay, let's take the example. This is the example we are going to discuss. Try to work out this problem. Okay, first read the problem and figure it out. Okay, a mold sprue is 20 centimeter long and the cross sectional area of the main runner is 2.5 centimeter square centimeter. The product cavity volume is as given, the 1560 cubic centimeter. Determine the following: velocity of the motor metal through the runner, the volume flow rate of the motor metal, and the mole filling time has to calculate. Okay, let's see how to solve this problem. Okay, then I will draw the mold. This let's take a example solution. Let's take this is the mold we are having, and this is the sprue. Then let's take the cavity area. I will draw the simple way. This is the cavity. Then this is the main runner. Okay. This is the mold. This is the cavity. This is the this is called main runner. Okay. The motor metal pour to this sprue. Then this motor metal passes to this cavity because of the gravity force. Okay, gravity force. Then when the motor metal reaches to this cavity area, then this cavity, while filling this cavity, the air trapped in this cavity escapes through the vent holes. Okay, vent holes. Okay, vent holes. Then how to calculate this one? First one. How to calculate the first one? How to calculate the first one? First one is asking velocity of the motor metal through the runner. So we have an equation to determine that velocity through the runner. V is equal 2g delta h into square root. All the data has given. We just want to substitute these values in this equation to find the value. The V is equal 2g 9.81 into delta h. Delta h is also given 0. I'll convert it to meters, 0.02 into square root. Let me find the value for this one. That is equal to the 1.981 meters per second. This is the velocity. This motor metal flow through this main runner. This is the velocity. Okay, this is the velocity. So then let's take a second question. The volume flow rate. What is the volume of volume? That means the Q dot is equal AU. The Q dot is equal A. Cross-sectional area also given 2.5. I am going to convert into meters. 10 to the power of minus 4 into velocity U. 1.981. Then the Q dot is equal again Q dot is equal 4.952 into 10 to the power of minus 4 cubic meters per second. This is how we are calculating the volume flow rate through the main runner. Then how to calculate the mole filling time easily? The mole filling time is equal total volume divided by the Q dot. That is equal to total volume 1.981. Sorry, total volume that is given 1560 in cubic centimeters. You have to convert into a cubic meters. 10 to the power of minus 6 divided by Q dot 4.952 into 10 to the power of minus 4 in cubic meters per second. So then the total volume, total mole filling time is, if we can calculate, is equal to 3.15 seconds. 3.15 seconds. Okay. This is how we are calculating the mole filling time in metal casting. Okay, metal casting. Next, we are going to discuss another important calculation related to the metal casting operations, the solidification time. Okay, solidification time. The solidification time calculation, that is also a very important calculation to design risers. This calculation is very important. Okay, to design a riser and also to ensure the mold has completely solidified, this calculation is very important. The total time taken, the total time required for the casting to solidify after pouring is called the solidification time. Okay, solidification time. So then what can you say about the solidification time? The total solidification time, we are calling as a total solidification time. Total solidification time. What can you say about this total solidification time? With the volume. For example, the comparing to the smaller size of a part and the larger size of part, what can you say about which part having the higher solidification time? Okay, this part, if the volume is high, it takes the longer time to solidify because this internal heat has to transfer to out. It takes a longer time to transfer because it contains the higher amount of heat energy. So the total heat energy have to release from the outer because it higher heat energy content, and also it has to transmit this internal heat to larger distance, larger thick walls. So it takes a longer time to solidify with the larger volume. So no doubt about that one. The solidification time increases with the volume. So sorry, there's a proportional relationship with the solidification time is proportionally related with the volume of the casting. If the volume is increases, solidification time also increases. Okay, solidification time also increases. So then what can you say about the solidification time with the surface area? Let's take this is the certain volume. This is the certain volume. Then it having the A1 surface area. Then the V1 volume. If we make into a thin sheet, the same volume V1, but it having the larger surface area compared to this situation A2. A2 is very much larger than A1. So which one solidify immediately? Okay, which one solidify immediately? Okay, this one, because it having the more surface to release the heat, internal heat. It can release the heat from the more surface area, so it can easily solidify before this part. So that solidification time is inversely proportional to the surface area of the casting. Okay, surface area of the casting. These are the basic relationship with the volume and the area of the casting, the solidification time. So then Chorionis has developed an equation based on this relationship. Chorionis has developed the equation called the Chorionis equations. Chorionis has developed the equation based on this relationship called the Chorionis equation in metal casting. Okay, in metal casting, the total solidification, according to the Chorionis rule, the total solidification time is a function the Cm V divided by A into N. V divided by A into N. This is the Chorionis rule. See the equation we are going to use to calculate the total solidification time. You can see that found a relationship also included in this equation. What is the relationship? Total solidification time is proportional with the power of V. You can see total solidification time is proportional to the power of n, and also the total solidification time inversely proportional to the surface area of the casting. Okay, you can see that it is inversely proportional to the e to the power of n. Then what is meant by this Cm? Cm is called the mole constant. Mole constant. Mole constant. Mole constant mean that is depend on the mole, type of material, the mole material, and also the features of the mole. This mole constant have to determine experimentally. For certain product, the mole constant have to determine experimentally. Okay, if you know the Cm, we can easily calculate the total solidification time, but we have to do certain experiment to find the Cm. Okay, in a practical situations, the Cm determined using the experimentally. So the n we are taken as the 2, that is depend on the type of casting. In most of the cases, n is taken as 2, usually taken as 2. N usually taken as 2. Okay, that is also depend on the type of casting. Okay, then this is the Torino's rule to calculate the total solidification time in metal casting. Okay, then let's take the example problem from this Torino's rule in metal casting. Let's take this one. Okay, this is the problem we are going to discuss. What will be the solidification time for 1100 millimeter diameter and 33 millimeter thick casting of aluminium? If the mole constant as given 2.2 second per square millimeter, then the take n as 2. The n value also given. If n value is not given, you can take the n as the 2. Okay. Then how to calculate that one? Let me take then let's see how to solve this problem. Okay. Example solution. This is what is the type of, what is the shape of the product? Okay, what is the shape of the product? It's a cylinder. It's a cylinder, no? It's a cylinder. The diameter as 1100 millimeter. R is equal 550 millimeters. Then the thickness is equal to 33 in millimeters. Okay. Then first of all, you have to calculate before what is the Torino's rule. Total solidification time is equal Cm V divided by A into power of n. Then first of all, we have to calculate the volume of the casting. Volume of the casting is equal to 5r square into h. That is equal to 5r 550 into square into 33. You will get the answer. 550 into square into 33. That is equal to 31 360 948. This is the total cubic millimeters of the casting. So then surface area. Then we have to calculate the surface area. Surface area is equal to cylindrical the two circular surface area and also the cylindrical part. That 2 5 r square 5 r square, then 2 5 r square plus 5 d h a is equal to 5 r square r 550 into square plus 5 diameter 1100 into h 33. Then a also we can calculate easily. It is equal to 14703.37 millimeter square. This is the total surface area. So then we can apply these values to a Chaurin's rule. Total solidification time is equal cm constant is given 2.2 that is the unit for that one, millimeter square. Then volume 948 divided by 214703.37 into 2. Total solidification time we can calculate. That is equal to 533.06 seconds. 506 seconds. This is how we are calculating the total solidification time in the metal casting operations. Okay. Then another important calculation we are going to discuss is the riser design. Next we are going to discuss about the riser design. I will explain the theory behind this riser design. Okay, riser design in metal casting operation. What is the purpose of the riser actually? Riser is used to avoid the shrinkage cavity defect in casting operations. So then I will explain the purpose of the riser. Let's take this is the screw. Then this is the main runner. Then it enters to the risers. It's a mortar metal reservoir. Then this is the casting. Let's take this is the casting. Sorry. This is the cavity area, product cavity area. Okay. Then this is the mold. Okay, mold. So where the mortar metal pour to this screw, then it passes to the main runner due to the gravity, and this riser fills with the mortar metal. Then this is fills with the part fills with the mortar metal. Then what is the purpose of the riser is riser keeps mortar metal until part is completely solidified. Okay, if there is no riser, what happens? Shrinkage cavity defect may occur. What is the shrinkage cavity defect mean? That kind of cavities are formed. This kind of cavities are formed because of the shrinkage. Okay, when solidifying the material, it gets shrink. So then, because of this lack of volume due to the shrinkage, it forms this kind of cavity at the top. This is called shrinkage cavity defect. So then, to avoid the shrinkage cavity defect, we are keeping this kind of riser. This is called riser. Okay, riser. The purpose of the riser is riser keep mortar metal until this part completely solidified. What it means, riser solidification time, that means the total solidification time of the riser should greater than total solidification time of the casting. Casting means this part solidification time. Okay. This is how we are designing the risers. Then as a norm, we are taken this value as the 1.25 times. That means total solidification time of the riser is equal 1.25 times the total solidification time of the part. Let's take that part. Yeah. Then as a norm, we are taken this value. The riser solidification time is 1.25 times the part solidification time. That means to get this solidification time, first we have to do the calculation for this one. We have to calculate total solidification time. If you know the dimensions, and also if you know the cm mole constant, we can easily calculate total solidification time for the part. Okay, then we have to multiply it by 1.25. Then we can get total solidification time for the riser. Required total solidification time for the riser. To get this solidification time, we have to decide what is the dimension for this riser. That means if we take the total solidification time of the riser, that is equal to cm v divided by a into n. Only thing we can change volume and the surface area. We can change. Okay, so that to get the required solidification time, here this one is a known value, cm is a constant, n also a constant. Only we can change the volume and the area. Volume and the area mean we can change only the dimensions of the riser. If you are normally we are taken as the cylindrical shaped risers. If you are fixing one certain particular dimension, that means if you are fixing certain radius for this cylinder, then we have to h is the variable to get this ratio. Okay, h is the variable to get this ratio. Then according to the required solidification time, we have to adjust the dimensions of the riser to get the required solidification time in riser design. Okay, then we can get this relationship. Then that means in after when solidification, lack of volume due to the shrinkage of the part, this riser can feed this lack of volume through this runner. Okay, through this runner. To compensate this lack of volume, riser can feed the molten metal. By keeping the molten metal, it can feed the molten metal. This is how avoiding the shrinkage cavity defect in metal casting using the risers. Risers, there's three different considerations when design the risers. What are these three? A riser should be able to keep molten metal until part completely solidified. First consideration. Second consideration, a riser should keep closer to the heavy mass area of the part. Riser should keep closer to the heavy mass area of the part. That means because the largest shrinkage occurs at heavy mass area of the part. Here you can see this riser is placed in a heavy mass area, not in here, because larger shrinkage happen in a heavy mass area, then it can easily suck molten metal from the riser because of the shrinkage. And also the second consideration is the riser should place closer to the heavy mass area. Then the third consideration, a riser should be able to feed enough molten metal to compensate the amount of shrinkage. Okay, riser should able to feed enough molten metal. That means it should able to keep enough molten metal. That means if the volume lack of volume due to shrinkage as the V, the riser should able to keep at this solidification time the greater than this volume. That means let's take this is the V2 let's take the V1. V2 should be greater than V1 when this part is completely solidified. That means riser should be able to feed enough material, enough molten metal to compensate this lack of volume. There's a three consideration. What are these three? I will explain again. Riser solidification time should be greater than part solidification time. Okay. Then second consideration, it should place closer to the heavy mass area of the part. Third consideration, riser should able to feed enough molten metal to compensate the lack of volume in solidification. Okay, these are the three considerations. To get these three considerations, we have there's a lot of calculation, but here we discuss only one consideration. That means solidification time calculation only we discussing here. Okay, I think you all got this clear idea about this riser design. Okay, this is all about the calculation related to the metal casting operation. Then we are going to discuss the last topic under this metal casting operations. Some defects, casting defects we are going to discuss. Okay, casting defects. Casting defects. Okay, so any manufacturing process associate the defects. So then here we are classifying these casting defects as the common casting defects and also the casting defect common for the sand casting. So first of all, we are going to discuss common casting defects. Common casting defects. First one, the misrun. Misrun. That means this kind of thing. Let's take this the riser. Then this is the cavity area. Okay. Without filling the cavity, it solidify inside the runner. Without that means without flowing into the cavity or without filling the complete cavity, it may solidify inside it. Okay, this is causes due to the poor this is causes due to the mortar metal solidify before completely this is called the mortar metal solidify before completely filling the mold cavity, called the misrun. That means the mortar metal solidify immediately without completely filling the cavity area, because there are two reasons for this one. Lower pouring temperature. Lower pouring temperature causes to solidify this mortar metal immediately when pouring. Okay, lower pouring temperature. The another reason, the cross-sectional area of the runner is too thin. Cross-sectional area of the runner is runners are too thin. These are the reasons for the misrun. Okay. The second casting defect we are going to discuss is the shrinkage cavity defect. This is common for all the casting operations. Misrun also common for all the casting operations. Next, shrinkage cavity defect. Shrinkage cavity defect. Then what happened in shrinkage cavity defect? The causes due to the solidification shrinkage. This kind of let's say this is the part. The in solidification what happened, this kind of defect formed, this kind of hole at the top. This is called shrinkage cavity defect. Shrinkage cavity defect. This kind of cavity formed at the top because of the solidification shrinkage. So how to avoid this one? How to avoid this one? We can introduce rises. Best method to avoid this shrinkage cavity defect, introduction of rises. Okay, introduction of risers in metal casting to avoid the. Okay, then what happened? The motor metal fills with the riser. Then after completing the filling, in shrinkaging, the lack of volume is sucked from the risers. Lack of volume can suck from the risers. You can avoid this kind of shrinkage cavity defect. Then next we are going to discuss. Here we are discussing only the few defects. There's a lot of defects. We are not going to discuss all the defects. The most common defect we are going to discuss. Okay, this is a common defect for all the casting operations. Next we are going to discuss casting defect common for the sand casting. Casting defect common for sand casting. The first one we are going to discuss the sand blow. Sand blow. What it means? Sand blow. In metal casting, this kind of cavity form after solidifying is called the sand blow. This kind of cavity form. This is called sand blow. Sand blow. What is the reason for this sand blow is? Reason for this sand blow is higher water content in the mold. Higher water content in sand mixture. Higher water content in the sand mixture, but it results the producing the steam. Then this stream trapped inside in pouring. The vent hole not able to escape this. Some situations they are not able to escape all the air produced inside the mold, so that this kind of cavity defects form. Then and also this also causes the poor vent design. Poor vent hole design. Poor vent design. Okay. That means this trapped air cannot escape, so that it accumulate in this kind of manner and it form the sand blow defect. This is common in sand casting. Second defect common for sand casting we are going to discuss is the penetration. Penetration defect in sand casting. The penetration mean after casting we can see this kind of rough surface which is some motor metal penetrate into the mold wall. Okay, let's say this is the mold wall. Then the mold wall, you can see this motor metal penetrate into the mold wall. Okay, penetrate into the mold wall. What is the reason for this one? Higher pouring temperature. Higher pouring temperature. Higher pouring temperature. Because of the higher pouring temperature, what happens? The viscosity of the molten metal reduces. Then this molten metal, when reducing the viscosity, this molten metal can easily penetrate into the cavities of the sand wall. That is the reason this penetration occurs. Then another important thing is lower compaction of compaction of compacting lower compacting of sand. If the lower compacting of sand mean if the lower compaction cause higher porosity inside the sand sand wall, so then the molten can easily penetrate into these porosities called penetration defect in sand casting. Then next one, third one, third defect we are going to discuss in common to the sand casting operation, pinhole defect. This is causes due to the pinhole defect mean if you take this just below to the surface of the finished surface of the casting, this kind of air bubble accumulate. This is because higher compaction of sand. Higher compaction of sand causes this pinhole defect because in metal casting, in sand casting, some amount of air can escape through the mold wall. The mold wall is a porous media. Some amount of air can escape through the mold wall. If the sand is highly compact, this cannot happen. So that air accumulate just below the surface of the wall. Then the second reason, poor vent design also. Poor vent design also causes to pinhole defect. Okay, pinhole defect. Then this is all about the theory related to the casting operations. Okay, we have complete all the theory related to the casting operations.